Hello everyone. Today we're going to look at Chapter 4, the beginnings of it anyway. Section 4.1 is exponential expressions. This whole chapter deals with exponential and logarithmic functions. So we are going to begin with exponential functions, as it says right there. So first of all, we have sort of the most classic example of exponential functions that you might ever see. Suppose that you get a job that pays you $2 on the first day, $4 the second, and $8 the third day, and so on. How much would you get paid on the 10th day? Well, we can go through and figure this out. So we've already been told that on day 1 we're paid $2. Day 2 is 4. Day 3 is 8. So then to see, make it a little neater 8 there, at least try to. There we go. To see what it's going to be on the 4th day, we sort of need to follow this pattern down. So if we get paid $2 the first, then 4, and then 8, what's happening here is that we're doubling each time. So double 18 to get 8 to get 16. Double it again is 32. Double it again, 64. Double it again is 128. And then again it is 256. 2 more times gives you $512, and finally the answer to the question, $1,024. Okay, so the drawback to it's pretty straightforward, right? Just multiply times 2. We can all do that. The drawback here is that we don't know what we'll get paid on, say, the 57th day, without knowing what we have to. Without knowing what we get on the 56th, and so on backwards. However, if you sort of look at this here, we have 2, that was our starting point. To get 4, we took 2 times 2. That's a multiplication there, believe me. Here we took 4 times 2, but remember 4 was 2 times 2, so this is already 2 squared, so 8 is 2 to the 3rd. And we can follow this all the way up, and we can check on our calculator that yes, indeed, 2 to the 10th power is 1024. Okay, so if we want a function that f of x that gives us the amount on day x, all we need to do then is just realize that the exponent matches the day. So this would be 2 to the x. So now we can see, for example, what we would get on the 20th day or the 56th day, as I said. Okay, so that's sort of the basic idea of an exponential function. We have a function in which the variable shows up on the exponent. That's sort of the defining characteristic. So let's look at some examples here. So we've already seen this function, right, for some of these values. We know that on day 1 it's 2, that's a 2, then that's 4, then it's 8. Working our way backwards, anything to the 0 power is 1, besides the number 0 itself. 2 to the first, remember here that 2 to the negative 1, with negative exponents we flip it, so this is really 1 over 2 to the first power, so that's a half. This is going to be 1 over 2 squared, or 1/4, and this is 1 over 8. So we can graph those. Don't forget this is really supposed to be a 2. So we can graph this. So 0 is at 1, negative 1 is a half, and I have a hard time drawing dots. Give me a second. Okay, I'm not sure how to draw dots. It's yelling at me. So we'll just continue on. So we have a half there, we have a 4th there, we have an 8th down here. Going this way, we have when x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. So we can try to draw a nice smooth line that goes through all those, something like this. Okay? I didn't do a great job, but just imagine we're going through here. As we move to the left, it sort of flattens out. Okay? So let's go over here. If we take 1/2 to the negative 3, don't forget that that means that we flip things. So this is really 2 to the 3rd, or 8. 1/2 to the negative 2, then again we flip 2 and put an exponent of 2 on it, so that gives us 4. This will be 2. That's again 1. This is 1/2 to the 1 power is just a half. You square 1/2, you get 1/4. And if you take 1/2 to the 3rd, you get 1/8. Okay? So one thing to notice here, remember, exponents are used for repeated multiplication. So as we move down this list, that's really like going to the right on the x-axis. So what that means is we're sort of repeatedly multiplying by a half. Well, what happens when you multiply by a half? Well, things get smaller. Just like over here, going to the right, we're multiplying by 2, and things get bigger. So if we start here, and at negative 2 it's 4, and that's supposed to be a dot. At negative 1 it's 2, at 2 it's 1, at 0 it's 1, at 1 it's a half, 2 it's a fourth, and 3 it's an eighth. So again, if we sort of try to draw a nice smooth curve, it's not supposed to go below the x-axis here, but it sort of flattens out. Okay? So we have the same basic shape. It's supposed to be, again, kind of a nice smooth curve there. And you can see this if you try to graph these functions on your calculator. Except in this case, it's going up and to the right. In this case, it's going up and to the left. Okay? So as we move down to the next slide, this gives us the basic shape for exponential functions. If b, the base of the exponent, so we're looking at here examples of f of x equals b to the x in cases where b is bigger than 1 and when b is less between 1 and 0. If it's bigger than 1, we are repeatedly multiplying by a number bigger than 1. So what that means is, if we, sorry, didn't mean to do that. If we're repeatedly multiplying by a number bigger than 1, things get bigger. So, I'm going to try to do a little bit better job drawing this. So it's going to look something like that. In this case, we're repeatedly multiplying by something between 0 and 1, so think of multiplying by things like 1/2 or 1/4 or 3/8. In this case, things are going to get smaller as you do that, but also remember that when you divide by a number less than 1, dividing makes the number get bigger. So that's why it's going up and to the left. And again, I apologize for the unsmooth curves, but hopefully you get the gist of what's going on. Up and to the left. So the question then becomes, why can't b be 1? We've covered every example for all positive numbers besides 1, positive numbers less than 1, positive numbers bigger than 1. Why can't b be 1? So I'll allow you to think about that. What happens when you change x when you have 1 to the x power? So consider that on your own. So from here, though, let's think about what's going on at the x-axis here. Notice if b is bigger than 1, as you move to the left, despite how I've drawn it, things get closer to that axis. And if b is less than 1, if it also sort of flattens out and gets closer to the axis here. Well, the x-axis forms what we call a horizontal asymptote. It's a really fun word, asymptote. Okay, so basically what that means is that's just a horizontal line that the graph gets closer and closer to without ever actually reaching. Okay, so the other thing to note here is that the point 0, 1 occurs on every basic graph because as long as b is not 0, b to the 0 power equals 1. Okay, so you can sort of see that. Again, I didn't do a very good job here. I missed the point I want on this right-hand graph, but this one I did a decent job hitting. Okay, so here's another thing for you to check yourself. On your calculators, graph y1 equals 2 to the x and y2 equals 3 to the x on the same screen. And then circle which one you think is steeper by looking at both of them. Do the same thing with these once you've decided on that. Okay? And then what I want you to do then is decide for yourself as b gets further away from 1, so as the base gets further away from 1, so notice 2 is closer to 1 than 3, 0.9 is closer to 1 than 0.2. So as the base gets further away from 1, does the graph get steeper or does it get flatter? Okay, so go ahead and pause the video. I'll wait, I promise, and see which one of those cases holds. Okay, you back? Good. So here we are, and we're looking at transformations of the functions, because really we can do a lot of graphing of these without actually using our calculator. So remember, we're looking at x to the 4 to the x power, and so remember that is this case where b is bigger than 1. So what that means is it's going to flatten out as you go left and get steeper as you go to the right. So it's going to look a little something like that. And I don't know why it keeps doing that, but it looks something like this where it curves as it goes up to the right. Okay, so then we just need to remember what happens when we apply specific transformations. So f of x is x to the 4th plus 2. That's the same basic function, except for now we're adding 2 to the output. And recall that when we add 2 to the output, what we're doing is we're making the outputs, or the y values, bigger by 2. So when you make the y values bigger by 2, you take all these y values that you used to have and shift them up. So this is a vertical shift up. Okay, so we're going up by 2. So we can always use this 0.01 that's on every basic graph, and we can use that as sort of our pivot point. So that's sort of our starting point. So if it's supposed to be at 0.1, we can move it up to 0.3. And then we have that. Also, don't forget that normally the x-axis is a horizontal asymptote. So this is something that's easy to forget. Do not forget to move the horizontal asymptote. So if that goes up by 2 as well, we're really looking at a new horizontal asymptote at y equals 2. So once we have that, all we do is just, again, take the graph, the shape of the graph that we have, and draw it there. Flattens out as it goes left, ramps up, and gets bigger as it goes to the right. Okay? So let's look at this transformation. Now instead of adding to the output, we're multiplying the output by a negative. So now what we're doing is taking all these positive y values we used to have and making them negative. So instead of at 0.1, we're at 0, -1. So we can go ahead and put that there. The horizontal asymptote doesn't move, so we just flip it over the x-axis. Let me try to do a better job on this right side. Oh, I'm not sure about that. Okay, so I did a fairly poor job. So let me start over. So flat on the left, hit the point 0, -1, and that's only slightly better. Okay, so there is the graph of -4 to the x. Notice we're not allowing the base values to ever be negative, and that's okay. This doesn't violate that because these are two very different things. Here is we're taking the number -4 to the x power. Here we're taking the number 4 to the x power, but we have a negative sitting out front. Those are two different things. Okay? So let's look at this then. If multiplying the output of a function makes it flip over the x-axis, multiplying the input of a function makes it flip over the y. So now we're taking these positive x values and making them negative, and these negative x values and making them positive. So that's going to flip over the y-axis. So that's going to look a little something like this. Flatten out as we go to the right. And so there again, it's this original graph flipped over the y-axis. So I left a blank here, so I have more to say. So one thing I want you to notice is that 4 to the -x is the same as 4 to the -1 to the x. Right? But also don't forget that 4 to the -1 is 1/4. So really, this graph that we started with can be written as 1/4 to the x power, changing the base, and you can see that this situation now holds. Again, I apologize, this should be a lot smoother and straighter, but we do see that it's going up and to the left. Oops, sorry, gone a little too far. Up and to the left and flattening out and getting smaller as we go to the right. Okay, so the last thing we have then is this function. So this one actually has two transformations. One, we're subtracting 2 from the output, so that's a shift down 2. We're also adding 2 on the input, or excuse me, adding 1 on the input. So that means we go to the left 1. Don't forget that shifts, horizontal shifts, are sort of counterintuitive. So since we're adding, we go to the left. So when we do that, we take this point 0, 1, we go down 2 and over 1. So it goes right there. Okay? It's right there now. So also don't forget, shifting the horizontal asymptote, taking the x-axis, this horizontal line, and shifting it left or right doesn't make a difference. However, shifting it down 2 very much does. So let's change and put that horizontal asymptote down lower like it should be. And now again, we're just ready to draw our graph. So the new graph looks like so. Okay? So there's our graph. Shifted it down 2 to the left 1. Alright, so moving on. These are exponential functions, so the properties of exponents here are very much important. So let's look at those. So first of all, this applies when we have the same base but different exponents. In that case, what we do, if you recall from the appendix sections, is we take the same base, in this case it's a, and we add the exponents. So the new exponent on a would be x plus y. Okay, so nothing new. Hopefully that's a review and it seems familiar. In this case, we have a base to a power, and that whole thing raised to another power. In this case, we multiply the exponents, so it becomes x times y. So let me try that one more time. A to the x times y, a little better. In this case, we have two bases inside here, so we distribute that exponent in. So this becomes a to the x times b to the x. Okay, this one, same sort of thing. When we have division or multiplication, in either case you can distribute the exponent. So this is a to the x over b to the x. And in this case, we can subtract the exponents. So again, this one is sort of analogous to another one. Here, if we're multiplying the same base, we add. If we're dividing with the same base, we can subtract. Okay? So in this case, here, number 21, we're just asked to simplify. So let's do that. This becomes 10. So notice we have the same base with different exponents, so we can add the exponents. So we have 3x plus a negative x gives us 2x. And we have a negative 1 plus 4 leaves us with a plus 3. Okay, so this becomes 10 to the 2x plus 3 power. This one's not so straightforward, but it's not so bad either. Here we're going to take this and we're going to apply this property right here, and we're going to distribute this outside exponent on here. So we have 4 to the x, and that's going to be raised to the 3z, over 5 to the y, also raised to the 3z. And now we use the second property to multiply these exponents. So this becomes 4 to the 3xz over 5 to the 3yz. Okay? And then finally what we can do is we can do a little simplifying here. We don't know what z, x, or y are, but we do know what 4 to the third power is. That's 64. And these other exponents stay to the xz over 5 to the third, which is 125 yz. Okay, so those are simplified. Again, that's just a little bit of a review from the appendix sections. Okay, so these other properties that we're going to be using. Basically, we can look at the graph of these exponentials, and despite my drawing, one thing that is in common with all of these is that they're all one-to-one functions. They all pass the vertical line test rather nicely, and they also pass the horizontal line test. So these are all one-to-one. So what that means is if the outputs are the same, the inputs had to have been the same as well. So here, that's what this is saying. If you have a to some power and it equals to a to some other power, the only way that's going to happen is if the two powers are the same. Likewise, if you have some base to x and some other base to x, those two are going to be the same if and only if the bases were the same to start with. Okay? So that gives us the ability to solve equations like this then. Here we see that 9 to this power is equal to 9 to that power. Well, the only way for that to happen is if the two individual powers, x squared and x plus 2, the only way that's going to happen is if the two powers are equal to begin with. So I've set the exponents equal to each other. Now we've got a quadratic. We can set it equal to 0. And there we have it. We have a quadratic we can solve. Thankfully, this one's factorable, like so, -2 and +1, leaving us to find the zeros of each of these factors individually. So this whole thing will be 0 if the first thing is 0, and that happens when x equals 2. And we also get a 0 when this second factor equals 0, and that happens when x is equal to -1. Okay? Okay. So, moving on then, we can do the same sort of thing. Here we recognize that we're going to be using this third property. We're going to be saying that since the exponents are the same, these bases had to have been the same to start with, and there's no problem there. So, 2x minus 1 must be, this base 2x minus 1 must be the same as that base x plus 3. So 2x minus 1 is equal to x plus 3. And this is just a linear equation, so I can subtract x, add 1, and cancel out where appropriate, here and there. 2x minus x is just x, and 3 plus 1 is, of course, 4. So we can see that if we plugged in x, 2 times 4 is 8 minus 1 is 7 cubed. 4 plus 3 is also 7 cubed, so 7 cubed is equal to 7 cubed. I don't need to know what 7 cubed is to know that both of these are equal to each other. Okay? Same sort of thing here. We can again recognize that these bases are the same. So if the bases are the same, again, we can set the exponents equal to each other and solve. So I'm going to go ahead and add 3x to each side. And I'm also going to add 6. Again, canceling where I can. That tells me that 8x is equal to 8. Dividing by 8 tells me that x should equal to 1. Okay? All well and good. So the potential problem comes in then for situations like this. Here it looks like we have neither thing, right? We don't have the bases are the same, and the exponents are not the same either. So what we can do here though is get a little tricky, and we can rewrite 4 as something that has the same base. So recall that 4 is 2 squared. So we can just retake 4 and write it as 2 squared. That's still all raised to the x squared power, and it equals 2x plus 3. So now if we look at this, go a few properties back, if we have this situation, we know we can multiply the exponents. So 2 to the 2x squared, make my x a little nicer, equals 2 to the x plus 3 And now we have bases that are the same, so we know that 2x to the 2 is equal to x plus 3. And now we know that 2x squared minus x minus 3 is equal to 0. And some trial and error will show you that this is actually factorable, which again is nice. So it factors as 2x and x. We also have to have a 3 here, so I think this is going to work out if we do this. So now if we just sort of check our work, 2x times x is 2x squared. Negative 3 times positive 1 is 3. But now if we look at this middle term, we get that by taking negative 3 times x, so that is negative 3x. This times that is 2x, so 3x, and 2x gives us a negative 1x. Okay? So this tells us then, again, we can solve the individual factors. This one's nice and easy. Plug negative 1 in there. What has to go in here? Well, we have to have a 2 in a denominator to cancel out this 2. And then what we have left has to be the opposite of negative 3, so that must be positive 3. And you can solve those individually if you're unsure of where those things came from. Okay? So we have the same situation here. Neither the exponent nor the bases are the same. We also don't have the advantage of just turning 27 into 9 to some power. However, we can reduce them both down to the third power. So this is 3 squared to the x. This, the 27, is 3 to the third. And take the other exponent along, x plus 1. Now again we can multiply, so this becomes 3 times 2x. Be a little bit careful here because we're taking this whole exponent times that whole exponent. So really this is 3 to the power of 3 times x plus 1. So now what we're going to do is we're going to take 2x equals this thing. Well, what is this thing? We have to distribute the 3, remember, so this becomes 3x plus 3. So I'm going to subtract 3 and subtract 2x, leaving us with x equals negative 3. Okay? All good there? I hope so. Let's move on. Compound interest. So this is one of the uses for exponential functions that we're going to run into. We're going to see a lot more in the next section. But this one deals with this equation right here. So we're dealing with compound interest. So here's the equation. A, the amount in account after time t, is equal to P, the principal or the initial amount invested, times 1 plus R over M, where M is the interest rate in decimal form. So it might be worth noting there. Decimal. Okay. M is the number of compounding periods per year, so that's how many times you get paid interest. So they're typically not going to tell you the number of compounding periods. They'll say it's compounded annually once a year, or semi-annually twice, quarterly 4 times, and so on. Okay, and then T is just the number of years. Okay, so let's assume that we're investing $3,000 in an account that gives us 5% interest, and we're going to wait 3 years. So let's see the different amount of money that we're going to get if we have things compounded at a different number of times each year. So if it's compounded annually, then M is equal to 1. So that's just 3,000 times 1 plus 0.05 to the third, because M times T is 3 in this case. So we have 3,000 times 1.05 to the third, and that gives us, 1 second, that gives us $3,472.88. Okay? So give me 1 second. I need to pause this. Alright, so we're back. Sorry for the delay. I had a upset 8-month-old that I had to take care of, but he has Cheerios and everything's okay. So let's look at this next example here. Now we're looking at monthly interest. So now the only thing that's changed with this example is that M no longer equals 1, it now equals 12 because the interest is compounded 12 times a year. So what that means is we have 3,000 the principal times 1 plus 0.05 over 12 times 3 times, or excuse me, to the power of 3 times 12. So now notice a couple things. One, this higher exponent is going to serve to make the overall number bigger. However, this fraction inside the parentheses is going to try to make the number overall smaller. So let's see which one of those two wins out. If we actually calculate this, what we get is $484.42. So it looks like, to me anyway, that we've got an extra $12 here. So it looks like that's going to give us, so it looks like that exponent's sort of 1, right? So let's see what happens if we bump this all the way up to M equals 365. So now, if we get daily interest, we should get more money. So let's see. So 3,000 times 1 plus, again, 0.05. And sorry, my decimal points aren't showing up. That's all over now 365. And it's raised to the power of 3 times 365. Okay? So again, this isn't. So let me try one more last time to get a 3 there. So there's our 3. So anyway, so again, this higher exponent should make the number a little bit higher. And it does. According to my calculation, we get now $3,485.47. So notice here, it went up, but not nearly as much. So it turns out that there's a limiting value, a factor here, so that you can increase the amount of compounding periods a lot. We could do it, say, every minute and every second and so on, but we're only going to get so much more money. Eventually that advantage is sort of going to go away, and we can kind of see that. Going from annually to monthly, we got $12 extra, but we only got about an extra $1 going from monthly down to daily. Okay, so this leads us into this idea of continually compounded interest. This is what happens when you are getting paid interest continuously, so like every second, every nanosecond, okay? So just for the sake of keeping things interesting or easy, what we have here is M. This is, again, the number of compounding periods. This is the same formula. That's Wes saying hello. The same formula is applying here, but we're going to assume that P is equal to $1 and R is equal to 100%. Okay, so as a decimal, just 1. So that just simplifies this equation. Now let's look at what happens when M gets really big. So yearly, this is where M is 1. So that should make sense. If you get paid 100% interest one time, that's $2. Monthly, that's 12. Every daily, that's 365 times. Hourly would be every hour, so 365 times 24 as an M value. But you can see it goes up, but it's going up ever so slightly. So if you keep going up past hourly to every minute or second, what you're going to see is that you get closer to this number 2.71828 and yada yada yada. That stands for Euler's number. So that's Euler with an E. So he came up with, he's the one that discovered this number, and this is used whenever growth is continuous. It doesn't have to be money in account. That's just anytime growth is continuous. And we're going to see some examples of that next in section 4.2, and you can see it right there. So that's 4.1. I hope you've enjoyed the video, and we'll see you next time for 4.2.